Hello students, GATE exam is very near now and I hope your preparation is going well. Students, in this last 1 month, put all your time and energy in studies and I'm sure you will get a very good results. The subjects of data structures, programming and algorithms are very important in context of GATE exam. Since last 5 years, after some subjects were removed from the syllabus of GATE exam, the questions from data structures, programming and algorithms have been asked for around 20 marks. So it's very important to prepare these subjects well. But there are some topics from which questions are frequently framed in GATE exams. So let's look at some of those problems from which questions are repeatedly asked in GATE exam. Let's read the problem first and then we will see how we will solve this problem. In this problem, they are saying, let A be an array of n integers sorted so that A1 is less than A2 is less than A3 and so on is less than An. Then they are saying, suppose you are given a number x and you wish to find out if there are indices k and l such that ak plus al is equals to x. Then they are asking us to design two algorithms for this. In part A, they are asking design an order of n log n algorithm for this problem. And in part B, they are asking design an order of n algorithm for this problem. So if we look at this problem, we are given a sorted array having indices from 1 to n. So what we are given? We are given an array of n elements. It's also sorted in increasing order. That is, A1 is less than A2, A2 is less than A3 and so on. Now, they are asking us that given a number x, we have to find two indices k and l such that the sum of a of k and a of l is x. Now let's see how we can get this output. In the question they are asking, we have to find if there are two indices ak and al such that ak plus al is equal to x. Now, for this to happen, what we can do is, we can take one element as k, a of k. Suppose we pick the first element as a of k. That is, we take a of 1 to be a of k. 1 is equal to k. Now what we are left with is that we have to find an element a of l such that a of k, that is a of 1 plus a of l is equal to x. Now, in the first part, they are asking us to design a order of n log n algorithm for this problem. Now, the moment you see that they are asking an n log n algorithm, what comes to your mind is n log n searching and sorting methods, divide and conquer, merge sort, quick sort. All these divide and conquer paradigm using techniques result in n log n algorithms. So what we will try to do here is, we will try to use the divide and conquer paradigm so that we can get an algorithm of time complexity n log n. So how we can get a divide and conquer paradigm using algorithm that results in this time complexity? So what we can do is, once we have this element a of k as a of 1, we will apply the divide and conquer strategy to obtain a of L. So using divide and conquer strategy, what we will do is, first we will divide the given array into two parts and obtain a mid element. So what we will get is a of mid is equals to a of n by 2. Now once we have this a of mid element, what we have to check is whether this a of mid element is our given a of n. So what we will do is, we will sum this a of mid with a of k to see whether the sum is x. Now in case the sum is x, we have obtained our answer. Mid will become n. But in case this mid is a of mid and a of k does not equate to x, then what we have to do? Now since we are using divide and conquer paradigm, we have to divide it into two parts. In divide and conquer paradigm, we have three parts. We have three steps or three stages to solve any divide and conquer problem. What are these three stages? First is divide. What do we do in the divide stage? We divide the given problem into some sub-problems which we are solving recursively. Then we obtain the solution of those sub-problems. This forms the conquer step. And in the third step, we combine. What we do is, once we have obtained the solutions from the second step, the solutions of the sub-problems, we combine them. We perform some operation on these obtained solutions so that we obtain the solution of the given problem, of the original problem. So this is the divide and conquer paradigm, and in the given problem, we have performed the first step, divide step. So from this step, we have obtained the value of mid and we have checked whether the solution for this mid is correct or not. In case the solution is correct, we will proceed and we will return mid as L. In case it is not correct, then what we will do is, since divide and conquer is a recursively applied design paradigm, so we will recursively divide. So what we have to do is, first we will check whether this value that we have obtained, a of L plus a of mid, whether it is greater than x or less than x. Suppose this results in a value that is greater than x, then what we are going to do? See, this is the given array a1 to a of n. What we obtained was a of mid. Now suppose this a of L plus a of mid is greater than x. Then what we need to do is, we need to search the array from a of 1 to a of mid, because the value of mid that we have obtained is resulting in a sum that is greater than x. And since the array is sorted in increasing order, in ascending order, so the desired value of mid or the desired value of L lies in the left part of the current mid. So what we will do is, earlier we had done mid as a of n by 2. Now again we will apply this recursively. So what we will do is, here new mid will be a of the current mid by 2. So this is the current mid, and when we divide it by 2, we will obtain the new mid. So we have now probed the left part of the array because the sum is greater than x. In case the sum had been less than x, then what we would have done? Then we would have probed the right part of the given mid. Why? Because the desired value of L would be lying in the right part. since the sum is less, the desired value will lie in the right part. Now, we will again check for this new mid whether the sum a of L plus given a of this k is greater than x, equal to x, or less than x. Now when we will check this, we will obtain either this a mid new plus ak is equal to x or less or greater. In case it is equal to x, then this new mid will become our L. And similarly, as we had previously done, we will repeat this step. If it is less, then we will probe the left part. If it is right, then we will probe the right part. So this is how we will use the divide step and conquer step. So like this, we will keep on going left, right in the given array, and we will obtain some value of L for which this sum would be equal to x. Now once we have obtained such a value, we have to return this value. Now in the question in the A part, they are asking that the time complexity of such an algorithm should be n log n. Now if the time complexity has to be n log n, what we need to do is, we have to first find the mid part. Now, we have found the mid part that will take order of log n time. Why it will take order of log n time? Because here we are dividing the given array consisting of n elements by 2. So, it will be log n base 2 divisions. We need to perform log n base 2 divisions since it is dividing by 2. And since this is asymptotic notation, we have to write it as order of log n. Now once we have this log n division cost, what we need to see is how much is the conquer cost and combined cost. So what we will do is, we will see that if this division has not resulted in correct answer, then what we have to do next. Now since this division can go how many times? This can go, since there are n numbers, we have to divide each time, and each time we will divide it, we will get a cost of log n. So how many times we can total divide until we reach the final answer? Since there are n elements, we can divide it by n times, and since the cost of one division is log n, dividing n times, the total time complexity would be n into log n. Now this time complexity that we have obtained is how we obtain using divide and conquer paradigm. This is the time complexity when we divide by 2, and keep on proceeding like this until we obtain the final answer. This is much better than the brute force time complexity that we would have obtained. How much time complexity would we have obtained had we done brute force method? If we would have done brute force, then what we would have done? We would have taken one element and checked with the remaining n minus 1 elements. So let's also see how this time complexity that we have obtained is better than the brute force method. In brute force method, we would have selected one element, and for that we would have compared with all the remaining n minus 1 elements. So how many additions we have to perform? For one element we have to perform n minus 1 additions. For one element, we have to perform n minus 1 additions, and in the worst case, if our answer is coming in the last comparison, last addition, then how many additions we had to perform before that? Before that addition, to reach that addition, we had to perform n into n minus 1 additions. For one element, n minus 1 additions. For n elements, n into n minus 1 additions. So n into n minus 1 additions, order of n square. So had we proceeded with the brute force algorithm, we would have obtained a time complexity of order of n square. But proceeding with divide and conquer algorithm, we have obtained a time complexity of n log n. Now in the question, this is the A part. They are also asking a B part, in which they are asking us whether we can improve this time complexity further. Is there any algorithm which can improve this time complexity from n log n to n? So let's see if there is such an algorithm. Now, of all the divide and conquer algorithms that we have studied, this happens to be the best time complexity. So we are forced to think whether we can look for any other paradigm, any other design paradigm in which the time complexity is better than n log n. So let's look at another design paradigm in which we get the time complexity as order of n. Now let's look at the greedy technique or greedy method to solve this problem. As you are aware, in greedy technique, we perform the solutions of optimization problems. What are optimization problems? Minimization problems and maximization problems are known as optimization problem. This problem also, we happen to get a sum, so this problem also can be solved using greedy technique. Now in greedy technique, the difference is that instead of checking all possibilities, like what we do in divide and conquer, what we do is we look for local optimum. We look for local maximum, local minimum, and then we hope that this answer should be correct. So what we will do here is, same thing we will apply. We will start with some element and we will obtain the local maximum, local minimum, so that we get the desired sum. Now in this question, we are given a sorted array. So what we know is that the first element is the smallest element and the last element is the largest element. In the question, they are asking whether the sum of any two indices k and l is such that it is equal to x. So what we will do is, first we will check whether the sum of the smallest index and sum of the largest index is x or not. But before that, if we want to make sure whether there are any such indices k and l whose sum is equal to x, then what we will do? First we will check the sum of the index n and n minus 1, whether it is equal to x or not. What we should expect is, we should expect that the sum of the indices n minus 1 and n, that is a of n minus 1 plus a of n, should be greater than or equal to x. If this is not true, then we can safely say that there are no such indices k and l for which ak plus al is equal to x. So this is the first check that we have to perform. Once this statement comes out to be true, we can go ahead and find. In case this statement is equal to x, that is a of n minus 1 plus a of n is equal to x, then what do we get our k and l? N minus 1 and n as it is. If this is equal to x, then k is equals to n minus 1 and l is equals to n. In case it is greater than x, then we need to find two such numbers k and l for which this statement is true. Now, in this case, where it is greater than x, one of the better methods to find out to such numbers k and l whose sum is x is that what we can do is we can keep the k as 1. We can keep the k as the starting index. And we can keep the L as the last index. So what we have obtained now is the sum of the smallest number and the largest number. And since the sum of the smallest number and largest number will be somewhere in between this, somewhere less than x, so what we will need to do is, if the sum is less than x, okay, then what we will need to do is, we will need to increase the k by 1. Okay. K is equals to 1 and L is equals to 10. This is how we start. If A of k plus A of L is less than x, if A of k plus A of L is less than x, then what we need to do is, we cannot increment the largest number more, but we can increment the smallest number more. So what we will do is, we will increment k by k plus 1. So here now we have A of k plus 1 and A of L. Now if this is again less than x, then we will repeat like this. We will keep on increasing k by 1 and we will keep on adding this number greater than the smaller number and so on, keeping L constant. Second case that we can encounter is this. Second case that we can encounter is that this sum is actually greater than x. If A of k plus A of L is greater than x, then what we need to do? What this means is that, see, k is the smallest indice, A of k is the smallest number, and L is the largest index, A of L is the largest number. Their sum is greater than x. So we cannot decrease A of k more because it is already the smallest number. But what we can do is, we can decrease A of L by 1. So it becomes a number smaller than the largest number. So in effect, what we are doing is, let me show you using this array. First, we add the first and last element, A of k and A of L. If it is equal to x, then we return them as it is. If it is less than x, then we go right. We increment k by k plus 1. If it is less than x, or if it is greater than x, then what we do? We decrement L. We move left. If the sum of first and last element is equal to x, we return as it is. If the sum of first and last element is less than x, then we increment k. If it is greater than x, then we decrement L. So either we increment k or we decrement k depending on whether the sum is greater than or less than x. Like this, we will obtain final values of k and L such that A of k plus A of L is equal to x. Now what we have to see is, what is the time complexity of this algorithm? We have seen two algorithms. Brute force has time complexity of n square. Divide and conquer has time complexity of n log n, which is the answer of part A. And now we will see what time complexity we get from greedy method. Now in greedy method, let's see how many additions we are doing. So we started with one value of k and l. So we did one addition. Now either we will increment k or we will decrement l. Again, in that iteration, we will do one more addition. Like this, at worst case, what will happen is either k will move to l minus 1 or l will move to k plus 1 or both will move to mid. In all three cases, how many times have we traversed the array? We have traversed the array only once. So how many additions we have performed? We have performed only n additions. So order of n comes out to be the time complexity of this algorithm. So how we are getting this order of n time complexity? Since we are traversing this array only once, either we are moving from leftmost end to rightmost end, or rightmost end to leftmost end, or from both ends towards the center. In all three cases, somewhere in the middle, we will meet. Both k and l will meet. In any of these cases, we have traversed the array only once. So what is the time complexity? The time complexity turns out to be order of n. So this is how we will solve this problem. We have three methods. The slowest and the worst method is the brute force method, in which we obtain time complexity of order of n square. Next is the divide and conquer method, in which we obtain the time complexity order of n log n. And third method is this method of greedy technique, in which we obtain the time complexity order of n. These are the three methods, and this is the solution of part A. Algorithm using divide and conquer: keep the first element fixed and perform binary search on second element. Jump from mid to next mid to next mid in the left or right, and that jump will take log n time each time. So it will be order of n log n. So this is the time complexity order of n log n of array using divide and conquer, answer of part A. And in answer of part B, we have seen a greedy algorithm that results in a time complexity of order of n. This is how we have to solve such problems. Now let's look at another problem. In this question, we are given a recurrence relation and we have to find the value of this recurrence relation. We are given a recurrence relation Tn is equals to 7Tn by 2 plus n square, and we have to find out what is the value of this recurrence relation. Now to solve recurrence relation, we have three methods. First is substitution method, second is the recurrence tree method, and third is the master method, master theorem. So we can use all three methods. Now in this problem, we will first solve using the substitution method, then we will also solve using the master theorem. So we can use recurrence tree method in case where we have more than one function calls in the right hand side. When we have more than one function calls in the RHS, we can use the recurrence tree method also. Now let's look at first the substitution method. After that, we will look at the master theorem. First, let's solve this problem using the substitution method. After that, we will solve it using Master's theorem. So, how we solve a recurrence relation using substitution method? In substitution method, we take the given function and we recursively substitute the value of that recursive function from the given relation. So, in this, Tn is equals to 7Tn by 2 plus n square. So, we have a relation between Tn and Tn by 2. So using this relation, we will find out what will be the value of Tn by 2 and substitute it in the place of Tn by 2 in this given equation. Let's see how we will do that. Now if T of n is 7T of n by 2 plus n square, what will be T of n by 2? T of n by 2 will be 7, this 7 is as it is, and we are substituting the value of T of n by 2 over here. So what is T of n by 2? If T of n is 7T of n by 2 plus n square, then T of n by 2 will be 7T of n by 2 square plus n by 2 whole square plus n square. So what we have done here? We have not done anything. We have just substituted the value of T of n by 2 using this relation over here. So this 7 is as it is. T of n by 2 is 7T of n by 2 square plus n by 2 whole square plus n square again as it is. So we have just substituted the value of T of n by 2. Now let's simplify this expression. So this is the simplified expression. Now we have T of n by 2 square. Let's find out what will be the value of T of n by 2 square, that is T of n by 4, and substitute it in the place of T of n by 2 square. Again we will use this given expression, and using that expression we will substitute the value of T of n by 2 square. So what is the value of this expression? Let's simplify it. So this is the simplified form of the given expression. So here we note that we can spot a series in this expression. So what we will do is, first we will find out how many steps of this substitution we need to perform in order that the value of n becomes 1. So here we see n is successively divided by 2. N, then divide by 2 it became n by 2, then again divide by 2 it became n by 2 square, then again divide by 2 it became n by 2 cube, and so on. So how many times we need to divide n by 2 until it becomes 1? So since it is successively divided by 2, so let's say n was some power of 2. Let's say n was initially 2 raised to power some k. Now, if n was 2 raised to power some k, then we can write n as 2 into 2 into 2 and so on, k times. So n was 2 into 2 into 2, so on, k times. Now, when we divide this expression by 2, what it becomes? 2 into 2 into 2, k minus 1 times. Now this is 2 into 2 into 2 and so on, k minus 1 times. Earlier it was k times. Once we divided it by 2, it became 2 into 2 into 2, k minus 1 times. Like this, successively we will divide by 2, it will become k, k minus 1, k minus 2 and so on. Finally, it will become 1 and then it will become 0. It was 2 into 2 k times, k minus 1 times, k minus 2, k minus 3 and so on. Finally, it became just 1 time, that is 2. And then again when we divided, it became 2 by 2, that is 1. So how many times we need to perform this division? So here you will note that until it became 1, k got subtracted by 1. From k, k minus 1, k minus 2, k minus 3. So finally k became, here k was 1 because we have 2 multiplied 1 times. So k is equals to 1. And when we divide it one more time, so k becomes 0. It becomes, the value of n becomes 1. So to make k 0, how many times we subtracted 1? To make k 0, we subtracted 1 from k, k times. K minus 1, k minus 2. Like that, in k steps, we subtracted all k's. All k. So k minus k became 0. Here k was 1 and here k is equals to 0. So when we subtract 1 from k, k times it becomes 0 and n becomes 1. So k is our value. Now what is the value of k? So here we have assumed n is equals to 2 power k. So let's see if we can use that equation to obtain the value of k. If n is equals to 2 power k, then what we can do is we can take log on both sides. If we take log of n base 2 is equals to log of 2 raised to power k. So what it will become? It will become k will come in front and it will become log of 2 base 2. Both sides we have taken log to the base 2. So on LHS we will have n log of n base 2 and it is equals to k. K into 1 which is equal to k. So we have found the value of k as log of n. Similarly, here we are dividing by 2 and so on until here also n becomes 1. So what will be the value of k? Here also we are dividing by 2. Here also we want n to become 1. So here also k will be log n base 2. So after log n base 2 steps, n will become 1. So here we will have obtained t of 1. N by 2 raised to power k, it becomes t of 1. And what will this expression become? This is 7 to the power 3. So here it was 7 to the power 1, it became 7 to the power 2, 7 to the power 3. So in third step it was 7 to the power 3. So in the kth step it will be 7 to the power k. So it will be 7 to the power log of n base 2. This is the coefficient of t of 1. Next we have a series over here. So how can we simplify this series? So we will note in this series we can take n square common. So if we take n square common, what is remaining inside? So here inside we have, see here we have no coefficient, so we can take it as 7 to the power 7 by 4 to the power 0. Here we have 1, so we have written it as 7 by 4 to the power 0. Then we have 7 by 4, so we can write it as 7 by 4 to the power 1. Then we have 7 by 4 to the power 2. Like this, we will have terms containing powers of 7 by 4. Now what will be the last term? So in the third step, when we have 7 to the power 3 here, we have 7 by 4 to the power 2. So after log n base 2 steps, when we have 7 to the power log n base 2 over here, we will have 7 by 4 to the power log n base 2 minus 1. If here it was 3, it was 2. If it is log n base 2, it will be log n base 2 minus 1. So here we have just written this series in reverse order. This series we have written it in reverse order. Once we have this series, let's see what further simplification we can perform. Here we have 7 raised to the power log n base 2. This, using a property of log, we can interchange 7 and n. So it will become n raised to the power log of 7 base 2. T of 1 is 1. So into 1. Next we have n square and a GP. This is a GP. 7 by 4 raised to power 0 plus 7 by 4 raised to power 1 plus 7 by 4 raised to power 2. This is a geometric progression GP. Let's see what we can do of this GP. The sum of n terms of a GP, there is a formula. First, let's note the formula over here. So the formula for n terms of a GP, sum of n terms of a GP is sum S is equals to A into R raised to power n minus 1 upon R minus 1. So the sum of n terms of a GP is A, that is the first term, which happens to be 1 over here, 7 by 4 raised to power 0 is 1, into R raised to power n. What is R? R is the common difference. So common difference we can see here is 7 by 4. 7 by 4 is multiplied in each term, 7 by 4, 7 by 4, 7 by 4 like that. Minus 1, R raised to power n, n is the number of terms, so we will soon see how many terms we have, minus 1 upon R minus 1. So let's see, let's put this formula here. So A is 7 by 4 raised to the power 0, which is 1, A into R raised to power n. So 7 by 4 raised to the power n. Now what is n? N is the number of terms. So how many terms we have? See, 1, 2, 3, so on up till log n base 2 minus 1. So from 1 to log n base 2 minus 1, we have log n base 2 minus 1 terms. Plus this one more term, 0. Plus this one more term. So log n base 2 minus 1 plus 1, which is log n base 2. So the total number of terms in this series will be log n base 2. R raised to power n minus 1 upon R minus 1. So this is the sum of the GP. Now let's try to simplify. So here we have n raised to the power log of 7 base 2. What is the value of n raised to the power log of 7 base 2? 2 raised to the power 2 is 4, 2 raised to the power 3 is 8. So log of 7 base 2 is somewhere between 2 and 3. So when you will calculate it, you will find out that log of 7 base 2 is equal to 2.81. So this term becomes n raised to the power 2.81. N raised to the power 2.81. Now let's find out the sum of this series. So here we have n raised to the power 2.81 plus we have n square, and in common we have 7 by 4 raised to the power log n base 2. So here also we will interchange n with 7 by 4. So we will have n raised to the power log of 7 by 4 is 2. Now what is the value of 7 by 4? So when you calculate, you will find out that Seven by 4 is equals to 1.75. When you will divide, you will find out 7 by 4 is equals to 1.75. So this will become n raised to power log of 1.75 to the base 2. What is the value of 1.75 log of and base is 2? So since 1.75 is smaller than 2, so 2 has to be raised to a power which is smaller than 1 in order for it to become 7 by 4, which is 1.75. This minus 1 and upon 1.75 minus 1. So here we have n raised to power 2.81 plus, okay, n square was common from here, n square was common from here, plus n square into, now 2 raised to power 7 by 4 is equals to 0.81 n square into n raised to power 0.81 minus 1, and in denominator we have 0.75. So both are constants, and in asymptotics constants can be ignored. They don't make any difference to the asymptotic notation. So here we have n square into n raised to power 0.81. So what will be the value? Since both bases are same, they are multiplied, both the exponents will be added. So what will be the sum? It will be n raised to power 2.81 plus n raised to power 2.81. Both these values are same. Both have equal power. That's why the answer will be n raised to the power 2.81. So this is how we solve this problem using the substitution method. Next, we will see how we will solve the same problem using Master's theorem. This is the solution using substitution method. Now we will see how we can solve this problem using substitution method. We can also write this as n raised to power 2.81 log of 7 base 2. Log of 7 base 2, we have written over here, log of 7 base 2 is equals to 2.81. Same way, we can write it as 2.81 or we can write it as log of 7 base 2. Now let's see how we will solve this problem using Master theorem. Now let's see how we solve this problem, how we solve recurrence relation problems using the Master theorem. So in the Master theorem, what we need to do is, first we need to express the given problem in the standard form. So in the standard form, we can write it as so here A and B are constants such that where A and B are constants and A is greater than or equal to 1 where B is greater than 1. So one interesting point here, A is greater than or equal to 1 is understandable. A can be 1 also and greater than 1 also. A is a constant. But B has to be greater than 1. B cannot be 1. Why B cannot be 1? It's an interesting point. B cannot be 1 because if B is 1, that means it's not a divide and conquer problem. It's not a divide and conquer problem. You have not divided. The number of terms are 1 only. That means you have not divided. and hence it's not a divide and conquer problem. That's why b has to be greater than 1. Now once we have the given problem expressed in the standard form, what we need to do next is we find out n raised to power log of a base b. We find out the value of n raised to power log of a base b, and then we compare it with fn. What is fn? Fn is this function. In this problem it is n square. In different problems fn will have different values. So we compare n raised to power log of a base b with fn, and according to that comparison we have 3 different cases. So in case 1 we have where fn is equal to, fn is less than n raised to power e. So here fn is equals to order of n raised to power log of a base b minus epsilon, where epsilon is a constant and it is greater than 0. In such case, what will be the value of Tn? Here Tn will be theta of n raised to power log of a base b. What is the value of Tn? Tn will be theta of n raised to power log of a base b. So one way to remember all the cases of master theorem, all 3 cases, is that Tn will be whichever is the greater one of n raised to power log of a base b or fn. Whether fn is greater, then fn will be Tn. If n raised to power log of a base b is greater, then n raised to power log of a base b will be the Tn. So now let's look at case 2. If fn is n raised to power log of a base b plus epsilon, in that case what we will do? In that case, since fn is greater than n raised to power log of a base b, fn is greater than that. So what we will do is, in that case, Tn will be theta of n raised to power, theta will be, fn will be theta of fn itself. Because fn is greater, so here Tn will be fn itself. And in case 3, if fn is equal to n raised to power log of a base b, that means both fn and n raised to power log of a base b both are equal. In that case, what will be the value of Tn? In that case, Tn is equals to n raised to power log of a base b into log n. In that case, Tn will be n raised to power log of a base b into log n. So now, once we know all the 3 cases, what we will do next is, we will find out that our given problem corresponds to which of the 3 cases of this, of master theorem, and according to that, we will decide which will be the solution. So these are the 3 cases. Let's see our problem corresponds to which. So we have A is equals to 7, B is equals to 2. So what will be? And Fn is equals to n square. Now from the given problem, we can see A is equals to 7, B is equals to 2, and Fn is equals to n square. Let's see what is n raised to power log of a base b. N raised to power log of 7 base 2. So this, as we have already seen, becomes n raised to power 2.81. This we have already seen. We have already calculated n raised to power 2.81. And what about Fn and its relation? So Fn is n raised to power 2. So what is the relation between these two? So we can say that Fn is equals to n raised to power log of a base b minus epsilon. Epsilon is 0.81. So when we subtract 0.81 from 2.81, it becomes n square, which is our Fn. So epsilon is equals to 0.81. Epsilon is 0.81. Okay, once we have this, we can see that this corresponds to case 1 of master theorem. So according to case 1 of master theorem, what is the value of Tn? The value of Tn will be n raised to power log of a base b. So Tn will be n raised to power log of 7 base 2, which is equals to n raised to power 2.81. So according to case 1 of master theorem, the value of Tn is equals to log of n raised to power log of 7 base 2, which is n raised to power 2.81. So we have obtained the same answer from master theorem which we obtained from substitution method. Both methods result in same solution, same answer. So this was the solution using master theorem. Okay. Now there is one more reason why this problem is significant. Sorry. This time complexity which we have obtained, n raised to the power 2.81, is a very important time complexity in algorithms subject. So when they ask this question, they can ask it like this also, and after asking to solve, they might ask that which popular problem does this solution correspond to? Which popular problem has the solution n raised to power 2.81? So in that case, what will be the answer? The answer will be Strasson's matrix multiplication. So the time complexity of Strasson's matrix multiplication is n raised to power 2.81. So after solving this, in further parts, they can ask that this solution corresponds to which problem? So the answer is Strasson's matrix multiplication. Earlier, matrix multiplication had the time complexity of n power 3. But Strasson made some efficiency improvement, some optimization to that algorithm, and brought the running time from n raised to power 3 to n raised to power 2.81. So this is one more question which they can ask in this problem. Now let's look at the next problem. Now let's look at the next problem. In this problem, they are asking match algorithms to the corresponding design paradigms. They follow. So here we have 4 algorithms. First is Floyd-Warshall's algorithm to compute all pairs shortest path. Second algorithm we have is quicksort algorithm. Third algorithm that we have is Dijkstra's shortest path algorithm. And fourth algorithm that we have is connected components algorithm. They have also given 4 design paradigms. First is greedy technique, second is dynamic programming, third is depth first search, and fourth is divide and conquer. So now let's see which algorithm will correspond to which design paradigm. First algorithm is Floyd-Warshall's all pairs shortest path algorithm. So we have seen that Dijkstra's algorithm is used for single source shortest path algorithm. Now Dijkstra's algorithm can also be used recursively to compute all pairs shortest path problem. But what would be the time complexity? That is the main thing. So we know that Dijkstra's shortest path problem Dijkstra's shortest path problem is used for single source. Now when we are using it for single source, the time complexity that we get is order of E log V. Now order of E log V is the time complexity which we get. Now if it is a sparse matrix, then number of edges is very less, or the graph is a sparse graph, then the number of edges is very less as compared to the number of vertices. But in case it is a dense graph, so the number of edges is close to that of a complete graph. In a complete graph, for V vertices, we have V square edges. So if it is a dense matrix, E can go up to V square. So in that case, what will be the time complexity? E tends to V square, E is order of V square. So the time complexity would be order of V square. Now, one method to compute all pairs shortest path is use Dijkstra's single source shortest path and use it for all the nodes, for all nodes as the source. So if there are n nodes, n vertices in the graph, we will apply Dijkstra's algorithm n times, selecting one node as the source each time. So if we have V vertices and for one vertex the time complexity is V square, what will be the time complexity for V vertices? For one vertex it is V square, so for V vertices it will be V into V square, which is order of V cube. So for single source we have V square, for all pairs it will be order of V cube. Now, this was one approach to compute all pairs shortest path. Now, Floyd and Warshall were two researchers who gave at the same time, simultaneously, they gave one method to compute this problem, to compute all pairs shortest path, but instead of Dijkstra, not like Dijkstra, they used dynamic programming. Dijkstra used greedy technique to compute single source shortest path, and we can use this technique repeatedly to find all pairs shortest path. But what Floyd and Warshall did, they used dynamic programming to compute all pairs shortest path. So what they do in Floyd-Warshall's algorithm is that they construct a table, they construct a matrix. So like in Dijkstra, we construct a table in which we mention all the distances, all the paths from the given source to all other vertices via all the other vertices. Similarly, in Floyd-Warshall's algorithm, we make a matrix from one node, second node, and so on, and in that matrix we compute from each node to every other node what is the shortest path. For example, if we have a graph with 4 vertices, let's see this graph. Suppose we have this graph A, B, C, D, and we have some edges. So what we will do is, first we will construct a table and we will call it A0. Now, what we represent in this matrix, what we represent in this table is that the cost from each vertex to every other vertex. So what we have here is, since we have no self loops, so the cost from every vertex to itself is mentioned as 0. Like that, when we will have the cost from all these edges, we will fill in this table. For example, if A to B is 2, here both places it will come as 2 and 2. Like this, for all edges, we will fill this table completely. This is how we will get A of cost from A, B, C, D to all other vertices. This is how we will get A of 0. Now, what we will do is, we will compute what is the cost from A to all, from all vertices to all vertices. But now what we will do is, earlier we had only considered the cost from vertex A. Now what we will see is via vertex B. For example, if we have to go from A to D, suppose the cost was 10. So what we would have obtained over here was 10. 10 here and 10 here. But now what we will see is, this cost is suppose 3, B to D is 3. So now what is the cost from A to D via B? It is 2 plus 3, 5. Now since this 5 is less than the given 10, we will update this value from A to D to 5. This 10 has been updated to 5. So this is how we have obtained this new table from the existing table. So this is how we will obtain edges, the values for this table from previous table for all vertices to all other vertices. Like this, we will get 1, 2 and 3. We will get 0, 1, 2, 3, 4 tables. And in the fourth table, what we would have obtained is, we would have obtained the minimum cost from all nodes as sources to all the other sources. So if we have 4 vertices, we have 4 into 4, 16 total costs. So in this table that we will obtain, the fourth table will give us the minimum cost from all pairs to all the other nodes. Now, in this technique, we have used dynamic programming. So what we have done is, we have explored all possible possibilities. Since we have explored all possibilities, this technique comes under dynamic programming. And next thing that we have to note about this is that we have only computed the distinct function calls. Unlike divide and conquer, where we compute the pre-existing function calls again, in dynamic programming, we don't do that. In dynamic programming, what we do is, we compute all the function calls only once. So, this technique would give us better time complexity as compared to the greedy technique. In greedy technique, we are getting order of V cube as the running time. In dynamic programming using Floyd-Warshall algorithms, it will be asymptotically equal to V cube only. Let's see here. Time complexity is equals to order of V cube for Floyd-Warshall's algorithm also, but it is asymptotic time complexity. The actual time complexity will be better than Dijkstra's order of V cube, because the reason for that is the code that we will write to obtain this cost using dynamic programming will be smaller and more efficient, and hence when practically implemented, it will be faster than Dijkstra's single source shortest problem algorithm. So the time complexity will be little bit less than that. So for this algorithm, we have obtained the answer as dynamic programming. So the answer for first option is Q. Now let's see the second option. The second option is quicksort. In quicksort, we use divide and conquer paradigm to solve this problem. What do we do in quicksort? We divide the given array using a partition method. Partition algorithm is an algorithm in which after each pass, the pivot element comes to its correct place. Let's see an example. In quicksort, we have an algo known as partition algorithm. What does the partition algorithm do? Partition algorithm picks any element which is known as pivot element, and what it does is, at the end of one pass of the partition algorithm, the pivot element that we have selected will come at its correct position, at its sorted position. For example, suppose this is the given array, and suppose we select the element 7 as the pivot element. 7 we have selected as pivot. So what will happen is, once we apply the partition algorithm, 7 will come to its correct position. So what will be the correct position of 7? Since there are 1, 2, 3. 3 elements which are smaller than 7. So 7 will come to the 4th position. So as we can see here, 7 has come to its correct position because all the elements on the left of 7 are smaller than 7 and all the elements on the right of 7 are greater than 7. Like this, at each pass of partition algorithm, the pivot element selected will come to its correct position. So if there are n elements, after n passes of partition algorithm, we would have each element sorted to its correct position. This is how quicksort performs the sorting using divide and conquer strategy. So the correct answer for this option will be divide and conquer strategy. Next is Dijkstra's shortest path algorithm. So we have already seen that Dijkstra's shortest path is used to find out single source shortest path. That means for each vertex of the given graph, it will compute what is the shortest path or what is the cost from that particular particular node to all other nodes via the minimum path. It will find out the minimum cost. So for that, what it will do is it will use the greedy technique. In greedy technique, what we do is, in greedy technique we find out which is the local maximum or local minimum. So we will select a node, let's say A, and we will create a table. Let's say these are the vertices A, B, C, D, E of a graph. Now what we have to see is how we can obtain the single source shortest path. Let's say the source given to us in the problem is A. Now since the source is A, what we will do is we will see that if source is A, then what can be the shortest path to others. So we will start this table by first mentioning the cost of direct edges. So if the graph has no edge to some vertex, then it will be represented as infinity, and others the cost would be represented. So first step is mentioning the cost of direct edges. Let's say there is no direct edge from the given source A to vertex B and D. So it will be represented by infinity. And if there are some direct edges, their cost would be represented here. Now what we will do is, we will implement it using a min heap. In min heap, all the nodes would represent the cost. So since we have a min heap, the root will represent the minimum. So what we will do is, we will pop the root and then we will compare whether that value is less than the given value. If that value is less than the given value, then it means that from the given source to some vertex, the cost via some other vertex is less than the current cost. So that vertex would be used to obtain the shortest path to that particular vertex. So using min heap, using binary min heap, this table would be completed and we will obtain the values. So what we will obtain is, the final value will be from source A, we will obtain the shortest path to all the vertices. So A to B, A to C, A to D, like this we will obtain the cost of all the vertices. Shortest path would be obtained using this table. So this is how we use the greedy technique. In greedy technique, we always compute the local optimum, local minimum, local maximum, and in the end we get the overall answer, and this is how we get the single source shortest path. So this forms the greedy technique, that is option P. And last we have connected components. Now how we find out connected components in a graph? In a graph, if we want to find connected components, what we do is, we first find out how many ways, first we see how many ways we can do it. We can use two ways, either we can use depth first search or we can use breadth first search to find out the connected components. How we use BFS and DFS to find out the connected components. So what we do in these two techniques is that we maintain an array called the visited array. Let's say the given graph has 5 vertices A, B, C, D and E. So initially what we will do is we will represent the cost, we will represent a flag 0 in all the 5 elements 0, 0, 0, 0 and 0. So in this array, this denotes that none of the vertices have been visited. Then we will start BFS or DFS over this array. Now we can start from any of the vertices. From whichever vertex we start, we might get some of the vertices covered. For example, A and C are covered. So we started from A and we could reach to C. So we have got one connected component. So what we will do next is we will check whether there are any other remaining zeros. If there are remaining zeros, it means that we have not covered the complete graph. Since we have not covered the complete graph, we need to run the algo once again, but this time we will start from some other vertex. For example, in this case, we can see that A and C were covered. Now what vertices are remaining? B, D and E. So this was the given graph. So what we will do is, in the first pass we got A and C. So we will run the BFS or DFS algorithm. We can use any algorithm once again and we will start from any of the remaining vertices. So we start, suppose, say from B vertex. So we can cover D and E. So their flag will also become 1. Now once their flag has become 1, it means no other remaining zeros are left. So in the first pass we covered 2 vertices, in the second pass we covered 3 vertices. Like this, there are no more zeros left in the array, there is no unvisited vertex. So we have covered all the vertices. So how many times we had to run this algorithm? In order to cover all the vertices, we had to run this algorithm 2 times. So 2 is the number of connected components in the given graph. So as we can see, this is one connected component A and C, and this is another connected component B, D and E. So in order to find out the number of connected components, we can use BFS or DFS. In the question they have given DFS. Had it been BFS, then that also would have been correct answer. And using this algorithm, we run it as many times as required in order to get all the nodes covered. So the number of times that we need to run the algorithm results in the number of connected components. So this is how we use DFS to find the number of connected components. Like this, we can solve such kinds of problems. It is a very frequently asked problem in GATE. It was recently asked in 2017, 15 and so on. So for these kinds of problems, we must cover the complete syllabus so that we can be able to answer such problems, because these problems are framed on complete syllabus. So you have to cover all the algorithms, then you will be able to know which algorithm uses which design paradigm. This is how we solve such problems. Now let's look at the next question. In this question, they are saying the correct order of efficiency of the following sorting algorithms according to time complexity. And they are comparing 3 algorithms: insertion, selection and bubble sort algorithms. So there are 4 options giving 4 sequences of insertion, selection and bubble sort algorithms. Now to compare these 3 algorithms, let's see what are the best case, worst case and average case running time of these 3 algorithms. So as we know that the worst case and average case running time of all these three algorithms is quadratic, that is the running time of all these algorithms in worst case and average cases order of n squared. Next thing that we have to see is what are the best case of all these three algorithms. So we know that in case of selection sort, even the best case is also order of n squared. So now we are left with the best case of bubble sort and insertion sort. So the best case of bubble sort and insertion sort comes out to be order of n. So this looks to be a tie over here between bubble sort and insertion sort, and selection sort is left behind. It is clearly the third most efficient out of these three. Now let's see this n and n, order of n, the best case running time of bubble sort and insertion sort in little more detail. So when we see it in little more detail, we observe that there are few cases or there are few ways in which insertion sort is better than bubble sort. So let's look at those cases one by one. Our first point is that in case of insertion sort, or rather in case of bubble sort, we always need to perform n comparisons in every pass. Okay. In bubble sort, whatever be the number of swappings that we need to make, still we need to make n comparisons. So the first reason why insertion sort is better than bubble sort is even in the best case, bubble sort definitely has to make n comparisons in every pass, whereas in case of insertion sort, it might be less than that. This is the first reason. Bubble sort always has to make n comparisons, whereas in case of insertion sort, it's not always n comparisons. In best case, it might be less than that. Second point why bubble sort is not as good as insertion sort is that in case of insertion sort, when the array is sorted, we directly have the sorted array. But in case of bubble sort, we need one more pass in order to obtain the sorted array. So second reason is one extra pass is required after sorting. So this is the reason why bubble sort is not as efficient as insertion sort. And the third reason why bubble sort is not as efficient as insertion sort is because in case of bubble sort, once we have obtained the sorted array, there is one case in which insertion sort is still better. In this case, if the given array or the given list has only one element that is not sorted, if only one element needs to be sorted, then insertion sort and bubble sort perform in different manner. Let's see how. If such is the case, then bubble sort will take, if for one element, bubble sort will take 2n time. And what will insertion sort take? Insertion sort will take same n time. Similarly, if two elements have to be sorted, then bubble sort will take 3n time, whereas insertion sort will take only n time. Like this, for some number of elements, we can obtain the time required by bubble sort and insertion sort, and we can see that this time is more for bubble sort and less for insertion sort. So this is the third reason why in the best case, insertion sort performs better than bubble sort. So we can obtain that final time complexity of insertion sort, bubble sort and selection sort like this. Insertion sort is more efficient. Insertion sort efficiency is more than bubble sort, and bubble sort efficiency is more than selection sort. So we have seen that in the best case, there is a difference between the three. For worst case and average case, all three are equal. But comparing the best case performance, insertion sort is more efficient than bubble sort is more efficient than selection sort. So this is how we have to find solutions of such kinds of problems. We have to compare not just the worst and average case, we have to see which algorithm performs best taking all the cases into account. So this kind of questions are frequently asked in GATE because they combine all the sorting techniques into one. So to be able to answer such kinds of questions, we must perform comparative study of all algorithms. Studying them individually is important when you are learning them, and to be able to answer such questions, you must perform a comparative study, which is also as important as studying the algorithms individually. So the answer is this. Now let's look at the next question. In this question, they are saying a hash table of length 5 uses chaining. What is the probability that at least 2 values are hashed into the same slot after 3 insertions? Now, first thing that they have told is that the hash table has length 5. So it has 5 slots. So this is the given hash table. It has length 5. It has 5 slots. Next thing which they are saying is that it uses chaining. So when it uses chaining, what it means is that suppose we have entered a value, let's say 2 over here. Suppose we have entered a key over here, and next the key comes again to this same index. Let's say this has index 0, 1, 2, 3 and 4 like this. Next key also comes to the same slot. So since chaining is used, what it means is that it will be stored here only in this slot using a linked list. Let's say the next key was, say, 12. So 12 is also stored in the same slot using chaining. Next thing that they have mentioned in the question is that they have performed 3 insertions. They have performed 3 insertions, and they are asking that after performing these 3 insertions, what is the probability that at least 2 of the keys have been stored in the same slot. Now, to get the answer to this kind of problem, what we need to see is, first thing is that what is the probability that each key was stored in a different slot. So first let's see what is the total possibilities. Now as we have seen that chaining is allowed in this hash table. In this problem they are using chaining. So if they are using chaining, the number of possibilities for first insertion is 5. Number of possibilities for first insertion Why number of possibilities for first insertion is equal to 5? Because there are 5 slots. So first insertion can be in any one of these slots. So number of possibilities for first insertion is 5. Next thing which they are saying is that chaining is allowed. Now since chaining is allowed, number of possibilities for second insertion is also 5. Why? Because since we can use linked list, so even though we have stored an element over here, the second element can also be stored over here, and third element, fourth element, all elements can be stored in the same slot using chaining. That's why since chaining is allowed, we can use the linked list to store all elements referenced to the same slot. Now next thing, we have seen number of possibilities for second insertion is also 5. Similarly, for n insertions, for all insertions, number of possibilities would be 5, 5, 5 and so on. So, in the given question, they are asking only for 3 insertions. So, the possibilities for third insertion is also 5. So, what are the total possibilities for 3 insertions? So we can see here that the first insertion could have been in any one of these slots. So total 5 possibilities. Following this first insertion, second insertion could also be in any one of these slots. So that also has 5 possibilities. And similarly, once 2 insertions have been made, third insertion could also be in any one of these slots. So for that also 5 possibilities. So total number of ways in which we can make 3 insertion is 5 into 5 into 5 ways. Five into 5 into 5 ways of making 3 insertions, which comes out to be 125 ways. Next, let's see if chaining were not allowed. If chaining were not allowed, then what could have been the number of ways? What could have been the number of ways? So if chaining was not allowed, for the first insertion, we would have had 5 possibilities. Now, in case chaining was not allowed, or we can say the same thing in a different manner. What we can say is that if suppose the hash algorithm is such, the hash function is such that we always get a different slot, a new slot for every insertion. In that case, what would have been the number of ways such that the elements would have hashed to different slots. Now, if the elements are hashing to different slots, for the first insertion, we have 5 possibilities. Now, since we have an element stored and we want each insertion to happen in a different slot, so this slot is gone. Now we have 4 remaining slots and second insertion should happen in any one of these 4 slots. So how many possibilities are there? 4 possibilities. So for second insertion we have 4 possibilities. Similarly, for third insertion, since we have now been left with 3 slots, 3 empty slots, so we have 3 possibilities. So if chaining is not allowed, or if all keys hash to different slots, then in that case we have 5 into 4 into 3 possibilities. Now in the question they are asking, what is the probability that after performing 3 insertions, the remaining 2 keys hash to same slot. Now we have seen what are the possibilities that all 3 insertions happen in same slot, and what are the possibilities that all 3 insertions happen in different slots. So what will be the probability that after performing 3 insertions, 2 coming keys hash to the same slot. So that will be the total number of possibilities minus the number of possibilities for 2 keys hashing to say 2 different slots. So what we will obtain here is, this we have obtained as 5 into 4 into 3 is equal to 60 possibilities. 60 possibilities of 3 keys hashing into different slot. Next, they are asking what is the possibility that performing 3 insertions, 2 keys hash to the same slot. So that would be total number of possibilities minus the number of possibilities of keys hashing to different slots. Let's note it down. So what we have here is possibilities of hashing to same slot. Possibility of hashing to same slot is equals to total possibility or total probability minus probability of hashing to different slots. So these both things we have calculated. We have calculated the total possibilities as 5 into 5 into 5, which is 125, minus probability of hashing to different slots, that we have calculated as 5 into 4 into 3 as 60. And since this is probability, we have to divide it by total number of possibilities, which is 125. So 125 minus 60 comes out to be 65. And in denominator, we have 125. So when we divide this, we obtain 13 by 25. This is the value that we obtain as the possibilities of 2 keys hashing to the same slot after performing 3 insertions. So this is how we have to find the possibility or the probability of keys hashing to same slot. But what we have to keep in mind is that sometimes in case of calculating probability, it is not easy or it is not viable to calculate the probability directly. In such cases, what we do is we calculate the probability of that case not happening. Like in this problem, we have calculated the probability of the event of hashing to same slot not happening. That is, we have calculated the probability of happening of hashing into different slots. Then what we do is we subtract that probability from the total probability and obtain the probability for the given case. So in this case, we have subtracted the probability of hashing to different slots from the total possibilities and obtained the probability of hashing to same slot. Like this, we have to solve such kinds of problems. So for hashing, it is very important to know not just the concepts of hashing but also the concepts of probability, because in many problems which are asked in GATE, they combine the concepts of hashing and probability and ask a combined concept, multi-concept problem on both these concepts. This is how we have to solve such kinds of problems. Now let's look at the next question. In this question, they are saying, consider a linked list containing n nodes where each node contains 2 pointers, pointer 1 and pointer 2. For each node, pointer 1 points to the next node of the list. Describe how pointer 2 should be set up for each node so that you will be able to locate the ith node from the start node in the list, traversing no more than log of I plus I by 2 nodes. So it's a very interesting problem. Let's see how we have to solve this problem. In the question they are saying that we have a linked list in which at each node we have 2 pointers. And in the question they are saying that pointer 1 points to the next node. So pointer 1 of all these nodes is pointing to the next node. So let's say this is node 1, node 2, node 3 and node 4. So the first pointer of all these nodes is pointing to the next node. Now in the question they are asking us that how we should design the pointing of second pointer. How should the second pointer be assigned so that for traversing to any ith node we have to make, first thing is floor of log I and second thing is I by 2 moves, not more than this moves. In the question they are saying not more than these many moves. So what we have to see here is we have to see how the pointer 2 should be assigned. So when we say log I, the first thing that should come to our mind is divide and conquer paradigm. Because in divide and conquer paradigm, we always recursively divide the given problem into subproblems. And whenever there is division process involved, the time complexity is in terms of logarithms. So the first thing that should come to our mind is log is divide and conquer whenever we see log. So let's see if we can use divide and conquer paradigm to develop some algorithm in which we get this time complexity. So if we use divide and conquer, what we will do is, since we are traversing, we are not dividing, since we are traversing, here what we will do is, the analogy of traversing to dividing is jumping. If we had a given big problem, a big array, and we had to find a small part, say one element in that array, then we would have divided that big array into small arrays. But here we are starting from one point, we are starting from one node, and we are covering the entire linked list. So this is reverse of dividing, this is covering. So in dividing, we divide by 2, so in traversing, we will multiply. So we will start with node 1, then we will jump. Multiply means to jump. So here we will jump by 1 node, then we will jump by 2 node, then we will jump by 4 node, and so on. So let's try to design an algorithm in this fashion. Start from 1. Whole this design process is for pointer 2. Start from first node. First cover one element. So covering one element means first pointer will point to node 2. Pointer 2 of this will point to node 2. Next, once we have covered one element, now we will jump by 2. Jump 2. So what will the second pointer of this node cover? It will jump. So it will not connect to 3, it will connect to 4. Now we have reached pointer 4. So what we will do is, now we will jump 4 elements. So since we are jumping 4 elements, the second pointer of node 4, it will connect to node 8. So the second pointer of node 4 has connected to node 8. So in this way, we are designing the second pointer. First it jumps 1 node, then it jumps 2 node, then 4 node, and so on. It will keep on jumping by an amount that is multiplied by 2. So let's see what is the time complexity that we get to reach ith node. Let's say I is 100. If I is 100, what are the values that we will get? First we will reach the second node, then we will reach 4th node, then 8th. Like this, we will reach the 2 to the power, we will reach all the nodes occurring in power of 2. So first we will reach the first node. Using second pointer, we will reach the first node, second node, 4th node, 8, then 16, then we will reach 32, 64, 128. So like this we have reached the 128th node. Now once we have reached the 128th node, we know how many steps we have made. We have made 1, 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, 2 to the power 7. So we have made 7 plus 1, 8 steps. So from the number of steps that we have made, we can deduce at which node we have reached. We have reached the 128th node. So now what we will do is, we don't have to go to 128, we have to go to 100. So what we will see here, we observe that the difference between 64 to 128 is 64. The difference between these two is 64. And we need to reach to 100th node. So 100 is 40 over here. So what we can do is, using this second pointer, first we reach the 64th node. Once we have reached the 64th node, then we will reach from 60 to 100 using the first pointer. So what is the total number of moves that we had to make? Total number of moves, as we can see, I here is 100. So what is log I? Log I is only log I is 6 point something, because 2 raised to the power 6 is 64 and 2 raised to the power is 128. Now they are saying that we have to take floor value of 6 point something. So it will be equal to floor of this, which is equals to 6. Next thing that we have is I by 2. So I is 100. So I by 2 would be equal to I by 2 will be equal to 50. Now once we have these two values, their sum is 50 plus 6 is 56. So we are allowed to make 56 moves. By now we have made only 6 moves and we have reached node 64. Now to move from node 64 to node 100, we have to make 36 more moves using pointer 1. So total number of moves in reaching from node 1 to node 100 is 36 plus 6, which is equal to 42. So we had to make only 42 moves using pointer 1 and pointer 2, and we reached the node 100. So this 42 is less than the allowed limit of 56. So yes, we can see that our algorithm is working for this problem. So we use pointer 2 in such a way that it jumps to 2 nodes every time. But this much, getting this answer for only one value is not sufficient. What we must do is, we must check whether this approach is working for other values also. And we must also see the pattern which we obtain for different values of I. So let's see. For next value of 2 to the power 7. So 2 to the power 7 is 128. Let's see for next value of next power of 2. Now next power of 2 is 8 and its value is 256. So now let's see what is the answer that we get for 256. Now when I is 256, what we will do is, first we will use second pointer to reach, when the I is between 128 and 256. What we will do is, we will use the second pointer to reach 128. So what we have done is, we have consumed 7 moves. So 7 moves have been consumed using pointer 2. And we have reached 128. Now, what can be the maximum that we can reach? Or what can be the maximum limit that we are allowed? So here, let's see. Log I we have obtained as 7. And what can be the maximum value of I by 2? Even if I is 255. Let's say I is 255. So, what is the value of I by 2? I by 2 is somewhere around 127 to 128. Now we have obtained the value of I by 2, that is 127. Next thing that we have to check over here is what is the sum of this 127 plus 7. So it comes out to be 134. 134 is the value that we are obtaining as the total range. Once we have obtained this 134, let's see how many moves that we are about to consume using this. So once we have reached using 7, let's see how much moves are left here. Now going from 255 to 128. 255 minus 128, it will be 127 moves. So 127 moves have been consumed using single pointer, and 127 moves plus we have those 7 moves that have been consumed using double pointer. So it again comes out to be 134. So we have got an exact answer, that is the worst case answer we have got. Even if we have to move to slot 255, even if I is equals to 255, what we do is first we use the double pointer and come to 128 consuming 7 moves only. Then from 128 to 255 we consume 127 moves and reach using the single pointer. So the total number of steps consumed, total number of steps is same as what is the maximum limit, 127 plus 7, 134, and here also our algorithm is returning 134. So our algorithm is taking as much time as has been asked in the question. So here we can see that for whenever we increment the value of 2, the power of 2 by 1, we get the same answer as is the limit. So this is how we have to design such an algorithm using divide and conquer paradigm. So the answer for this question will be, using divide and conquer, we assign the second pointer to jump number of nodes always increasing by 2. This is how we can design this algorithm. Now let's see the next question. In this question, they are saying consider the following code fragment. Int mystery struct tree node star root. If root is equal to null, return 0. Return 1 plus mystery root left plus mystery root right. What does the above code return for the below tree? So as we can see in this code, first thing is that we have been supplied with a pointer called root. Now root is a pointer of type tree node. So tree node is a structure and root is a pointer of that type. So what we have obtained is, we have obtained the pointer to the root of this given tree. Now once we have the pointer to the root, that means we are starting this code at this node, node 63. Next thing is that if root is equal to null, next they are comparing if the root element has value equal to null. Since we can see here root is not null, next thing they are saying if root is null, return 0. Otherwise what they have to do is return 1 plus mystery root left plus mystery root right. So what we can see here is this root is not null. So what we will do is return 1 plus mystery root of left mystery root of right. So when this comes, we see that this is a recursive function call. Since mystery is calling mystery again, and that too 2 times, this is a recursive function. Mystery calling itself 2 times, it's a recursive function. Any program, any function which calls itself is known as a recursive function. Second thing that we are observing here is that this is a tree traversal program. In this program, we are traversing a tree. So let's see how we will use this recursive program to traverse this tree. So when we start from 63, we see that 63 is not equal to null. then what we do is, this mystery calls another mystery root left. So this mystery will call 43, and then again this will start. Let's see the recursive stack for this program. Whenever we get a program which is using recursion, we must clearly solve it using recursive stack. So mystery of 63 is called, it is being solved using recursive stack. So let's draw the recursive stack. Mystery of 63 is calling 1 plus mystery of roots left. 1 plus mystery of, now what is root left? Root is 63, root left is 43. Plus mystery roots right. What is roots right? That is 16. So mystery of 63 called 1 plus mystery of 43 plus mystery of 16. Next we have to see what these two function calls will call. Now mystery of 43, when this function call is called, it will again call, it will first check whether it is equal to null or not. Since 43 is not equal to null, it will call 1 plus mystery of root left, that is 18, and 1 plus mystery of root 32. Mystery of 43 is calling 1 plus mystery of 86 and 1 plus mystery of 32. 1 plus mystery of 86 plus mystery of 32. But still we have mystery of 16 remaining. So it is up to us whether we want to represent it here or we can represent it somewhere else. So in order to avoid confusion, let's represent it somewhere else. So this is the representation for mystery of 16. What will mystery of 16 call? It will call 1 plus mystery of, since there is no left, there is only right, 1 plus mystery of 9. Mystery of 16, 1 plus mystery of 9. Okay, now we have mystery of 86 and 32. What will mystery of 86 call? 1 plus mystery of left and mystery of 9. 1 plus mystery of its left and 1 plus mystery of its right. Since there is no left, no right, it will only be returned by 1. So let's see, this becomes since there is no left, no right, it will be only 1 like this. So this one we have obtained from 86. Next we have mystery of 32. Now mystery of 32 will call 1 plus mystery of 95. So this we have obtained 1, and next we will obtain another one. 1 plus mystery of 95. Now let's make another recursive stack for this mystery of 95. It will be only 1 because there is no left child, no right child for this 95. Now we have this function called remaining, mystery of 9. Let's see what it will return. It has both a left child and a right child. So it will call two functions. So what will mystery of 9 call? It will call 1 plus mystery of 53 plus mystery of 64. Now let's see the function calls for 53 and 64. Sorry, since there is no child of 53 and 64, they both will only return 1. So this is how we draw 4 plus 1 5, 5 plus 1 6, 6 plus 1 7, 7 plus 1 8, 8 plus 1 9. So the answer for this will be 9. This is how recursive program will execute and traverse the given tree. Interesting thing to note here is that what this code is designed to do. This code is designed to add a 1. See, if the root is null, it is returning 0. That means it is completely ignoring the null nodes. It is completely stopping when there is no further node. Next thing what it is doing is, it is returning 1 whenever there is some child. That means for all those nodes which are existing, it is returning 1. And then it is again calling the same function for the left child also and right child also. So for each node, it adds 1 and calls the function for its child. So what it is doing in effect is that it is adding 1 for each node and passing on the code to the child node. Again, the child will add 1 for itself and pass the code to both its children. Like that, each node will add 1 for itself and pass the code to its child. So for each node in the tree, we will add 1. So the answer will be 1 added those many number of times as many nodes we have. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 nodes we have. For each node, 1 will be added. Code will be passed on to the child node. So total 9 addition of 1 and the answer will be 9. So here we get the answer as 9. So this is how we have to solve those problems which involve recursion and tree traversal, graph traversal. We have to recursively draw this recursive stack, and for each function call, we have to draw the stack and compute the value of the code. So we will get the value for the recursive program and we will also traverse the tree. Now let's see the next question. In this problem, we are given a C program and they are asking what is the output of the given C program. So as you can see in this given program, they are using arrays and pointers. So there are two concepts that are being used, arrays and pointers. Let's see how we have to solve such kinds of problems. So in the starting we see that there is an array A, int A, and it is storing the values 10, 20, 30, 40, 50, 60. So let's depict this array A, and store the values 10 to 60. So we have this array A and it is having values 10 to 60. Next, let's see, we have another array B, but it is int star B. Now, B followed by braces, B followed by brackets, it represents that it is an array. The name of the array is B. But it is also having int star. What does this int star mean? Star means that it is an array of pointers. Star means that it is an array of pointers. And what does int mean? Int means that these pointers which are stored in this array B, when we reach the destination or when we reach the data stored in the locations pointed to by these pointers, then there the data is integer type. That means B is an array of pointers to integers. The data lying at the storage where the elements of array B point, that is of type integer. Or we can say B is an array of pointers to integers. This is what is the meaning of this statement. Next, they have assigned some values to obtain the addresses which are to be stored in the array B. So here we have an array A. Let's say that the base address, the starting address of this array A is 1000. Now, since it is of type integer, since the data stored in this array A is of type integer, each memory element, or we can say that each slot of this array, it will store an integer. Hence, to store an integer, we need 4 bytes. We need 4 bytes to store an integer. So, when we are storing 10, 4 bytes would be reserved. So, which will be the 4 bytes that are reserved? 1000, 1001, 1002 and 1003. These 4 bytes would be reserved to store this element 10. So, 1 to 3, 1000 to 1003 are reserved for 10. So, for storing 20, the address from which the storing will begin is 1004. 1000 to 3 are used to store the element 10. For storing element 20, 1004 to 7 will be used. For storing 30, 1008 to 11 would be used, and so on. So each element will take 4 bytes and we will get the addresses of each of these elements. Like this, we have got the addresses of all the elements. Next, let's fill up the array B. So as we have discussed, array B is an array of pointers. So what will array B contain? Array B will contain addresses. Since it's an array of pointers, pointers are addresses to other memory locations. And it will contain addresses to memory locations which store data of type integer. Next thing we observe here is, we have A plus 5 as the first element of array B. Now what does this A plus 5 represent? A plus 5 represents that A here is the base address. So whenever we are supplied with the name of an array, what does it mean? Whenever we are supplied with the name of an array, it means that we have been given the base address of that array. So A here represents the base address of array A, which is 1000. A means 1000. The variable A, whenever it is supplied, it will reference to 1000. So here A references to 1000. Now what does this plus 5 represent? So A is a pointer, A is an address. Now since A is an address, what this plus 5 means is, since it's a pointer, in pointer arithmetic, whenever a pointer is added with a numerical constant, it signifies that how many places we have to jump, how many places we have to increment in order to get the resulting pointer, in order to get the resulting storage location. So that memory location which is pointed to by A plus 5 is actually A plus 5 memory locations. Now since the array A stores integers, each memory location, each slot occupies 4 bytes. So A plus 5 would be jumping 5 elements and reaching the next position. So A would mean that we are pointing to 10. What would A plus 1 mean? A plus 1 mean we are pointing to 20. A plus 2 would mean we are pointing to 30. A plus 3 would mean we are pointing to 40. A plus 4 to 50. And A plus 5 to 60. So what would A plus 5 mean? A plus 5 mean that jumping 5 locations. A would reference to 1000, A plus 1 1004, 2, 3, 4 and 5. So A plus 5 would reference to 1020. So the first element of array B will store 1020. Once we have obtained this one value, we can similarly obtain all these values. So what will a plus 3 store? See, a will store 1000, a will represent 1000, a plus 1 1004, a plus 2 1008, and a plus 3 will represent 1012. Once we have obtained a plus 3, let's see what a represents. A is directly 1000. Next is a plus 4. A plus 1, a plus 2, a plus 3, a plus 4 is 1016. Next we have a plus 1. A plus 1 is 1004. Last we have a plus 2. A plus 2 is 1008. Like this, we have completely filled the array B also. Next, what we have to see is, we have an element C. We have a variable C. Now, what does this variable C represent? It is declared as int star star C is equal to B. Now, this C is having int star star in front of it. What does this int star star means? 2 stars means that it is a double pointer. What is a double pointer? A pointer to a pointer is called a double pointer. Now what does this double pointer mean? Since it's a double pointer, it means that it points to a memory location, and at that memory location also there is a pointer. So the data at the location pointed by C will also contain a pointer. And since it's a double pointer, the data contained at that location, which is a pointer, when we reach the memory location pointed by that second pointer, we will reach a memory location that contains a data of type integer. So what a double pointer means, pointer to a pointer, and at the second location, when we dereference, when we reach, we find data of type integer. So what C will store is B. Now as we have discussed, whenever the variable name, the name of an array is supplied, it references the address of that array. So here we have array B. Let's say it starts storing from 2000. So since this is storing addresses, let's say that the size of these addresses is 8 bytes. Let's say that we have an architecture where the size of each address needs to be stored in 8 bytes. The size is such that it requires 8 bytes. So what would be the sizes? First 8 bytes would be reserved for storing this 1020. So it will reserve the memory locations from 2000 to 2007. Those would be the 8 bytes. Next 8 bytes from 2008 to 2015. Next 2016. Next 2024. Next 2032. And finally 2040. So this is how array B would be allocated. Once array B has been allocated, we know the base address, we can assign that to variable C. So the variable C stores the base address of the given array, which is 2000. Once we have the variable C with us, next thing that we have to see is which are the statements. So the first statement is C++. So that statement will increment C by one value. Now since C is a memory address, so what would be it increment to? It will not increment to 1000 to 2001. It will not increment by 1. It's not an integer. If it were an integer, plus 1 would make it 2001. But this 2000 is not an integer. It is an address. And since it is an address of an array which stores memory addresses, each consuming 8 bytes, so when it is incremented by 1, since it's a pointer incremented by 1, it will point to the next location. So increment by 1 and it will point to 2008. So incrementing it by 1 will make it 2008. So this 2008 is now the value of C. Let's note it inside so that we don't get confused. this is 2008. Next, what we are doing here is printf c minus b. So what is c minus b? C is storing b. C is storing the address of b, which is 2008. It started with 2000, incremented it to 2008. So now C is also a memory address. And what is B? B is also a memory address. B is the base address of array B, which is 2000. So C minus B is actually the difference of two memory addresses in the same array, that array being B. So it is 2008 minus 2000. So what is 2008 minus 2000? Whenever pointers are subtracted, see, these base addresses are nothing but pointers. These addresses are memory locations. These are the pointers. So whenever we are subtracting two pointers, whenever we are subtracting two addresses, what it means is that it does not mean the numerical value of the subtraction of those two numbers. It means what is the difference between this location and this location. What is the number of elements between the locations given by the two addresses. So first address is giving the location 2008 and second is giving the location 2000. So what their subtraction would mean? It would mean what is the number of elements between these two elements. So here we can see that there is only one element between these two elements. Or just to make it easy, just to understand it in a better way, what we can do is we can actually find out the difference between these two numbers and then divide by the size of each element in this array. When we do that, we obtain the number of elements. The difference between the numbers divided by the size. So in this particular array, the size of each particular element is 8. So 2008 minus 2000 by 8. So it will be equal to 8 by 8, which is equal to 1. So this is what is the value of star C plus plus or C minus B. This is the value of C minus B. So what is the first output that we are getting here? The value of C minus B we got as 2008 minus 2000 by 8, which is 8 by 8, which is 1. So the first output that we are getting is C minus B, which is 8. Oh, sorry, which is 1. 8 by 8, which is 1. Next thing that we are doing in this program is star C minus A. What is the value of star C minus A? So let's see what is star C. Star is the asterisk or the star operator. It is used to dereference. Now C is containing 2008. When star is applied, it dereferences 2008. So when 2008 is dereferenced, it returns the data of 2008. It returns 1012. So when 2008 is dereferenced, it will return 1012. What is done with this 1012? Star C minus A. So what we are doing is 1012 minus A. A is the base address, that is 1000. A is 1000. So what we are doing is star C is 1012 minus 1000. So 1000 minus 1000, 1012 minus 1000. Again, subtraction of pointers, subtraction of memory addresses does not mean subtraction of two numbers. It represents what is the number of elements pointed by these locations. What is the number of elements between those locations which are pointed by these two memory locations, these two addresses. It is subtraction of addresses. So performing subtraction of addresses, we will use the same concept we will obtain the numerical value and divide it by the size. Like that we will obtain what is the number of elements at these addresses. So here we obtain 12 and we divide it by size. Now since this is array A, what is the size of each element in array A? It is 4. So we will divide 12 by 4 and we will obtain 3. So as we can see that there are 3 elements from 1 to 12. 1 to 12 we are having 3 elements. This is how we have to obtain the difference of two memory addresses. So the second output that we will get here, which is for star C minus A, will be 3. Okay, let's see what is the third operation. Third operation here is star star C. So what is the value of star star C? C is storing 2008. Star C means dereference 2008. Get the data at 2008. So what is the data at 2008? 1012. Once we have got this 1012, one star is complete. But we have another star. We have 2 stars. So to complete the second star, we again dereference. We again get the data at this 1012. So what is the data at 1012? It is 40. So 40 is the output of this third operation. What does star star C means? Star star C means dereference C 2 times. C stores 2008. Once we dereference, we obtain data at 2008, which is 1012. Now we again dereference 1012. Dereferencing 1012 means get the data at 1012. What is the data at 1012? It is 40. So the answer is 40 for this command. So here we have obtained 3 outputs for 3 commands. Let's see the next command. Next we have star C++. Now one very important point that we need to remember about operators in C language is that whenever there are 2 operators operating on one variable, or whenever some operators are coming together, what we have to see is we have to see the associativity and precedence. Associativity and precedence are 2 concepts which we need to keep in mind while operating multiple operators. So when star and plus plus, that is the increment operator, and star asterisk, which is the dereferencing operator, when these both come together, we have to follow the precedence rule, which says that whenever these 2 are being operated together, always follow from right to left. Always follow from right to left. So let's note down the precedence rule. Star and plus plus increment operator always operate from right to left. So whenever we operate from right to left, let's see what is the output we get. So in the right we have plus plus, which is increment operator. So C++, what do we get? 2008, when it will be incremented, it will increment by 1 position, it will become 2016. This is not a number. 2008 is not a number that it will become 2009. It's a memory address. So when it's incremented, it will point to the next memory location. It will become 2016. Once we have obtained this 2016, next what we have to check is that what is the next operation, which is star. So what is star of 2016? So 2016 is here, and star C means what is the data at 2016? It is 1000. So what this value means is 1000. But there is no print command before this. Since there is no print command, nothing will be printed. We just incremented and accessed, but did not output it. So this statement is also complete. Next statement. Printf C minus B. Now C has become 2016, B is 2000. So what is C minus B? Let's solve. It will be 2016 minus 2000 by size. And what is the size? Size is 8. So it will be 16 by 8, which is equal to 2. 16 by 8 is 2. So this output will be 2. Next is star C minus A. So C is 2016. What is star C? Star C is 1000. And what is C minus A? Star C minus A, 1000 minus 1000. 1000 minus 1000 will be 0. So second output will be 0. Then again we have star C. So we have seen C is 2016, star C is 1000 and star 1000 is 10. So the output will be 10. So this is the output that we have got for star C. Let's see the next command. It is plus C. So what is plus C? It will make C from 2016, it will make it 2024. Okay. Next is star of plus C. Star of 2024. What is star of 2024? It is 1016. So we have executed till this point. We have got star of plus C. C is 2024. Star of 2024 is 1016. So we have obtained 1016. Now it is saying again plus. So what this 1016 will become? This 1016, now this is incremented and it becomes, from 1016 it will now become 1020. Now this is storing 1020. So this command is also over. Now let's see the next printf. It is C minus B. C is 2024 and 2024 minus 2000. So what will be the answer? 2024 minus 2000 and divide by size of B, which is 8. So it will be 24 by 8, which is equal to 3. So the answer will be 3 over here. Next we have star C minus A. What is the value of star C minus A? C is 2024, star C is 1020 and star C minus A, 1020 minus 1000. So what is the value of 1020 minus 1000? Let's see. 1020 minus 1000 divide by the size. Size is 4 over here. So the answer will be 20 divided by 4, which is equal to 5. So the next output will be 5. Once we have got this output, next command is star C. So C is 2024. What is star C? Star C is 1020. And what is star 1020? It is 60. So the next output is 60. Like this, we have to perform these operations and get the outputs. Let's see the next operation. Next operation is star C. So star C is 2020. C is 2024. Star C is 1020. Once we have reached 1020, it is saying plus. So again it will become C. Now our array A is declared up to 1020. In memory, whenever we declare an array of some size, then we reserve those many positions. Outside those positions, we can have any data from the previous programs. We have some garbage data. So here we have some garbage values outside of 1020. And once we are increasing plus, so what we have done is, first we have reached C is 2024, we reached star C 1020 and we incremented this 1020 plus 1020. So what this will become? See, this will become 1024. Since the size is 4, it will become 1024. But when we do this star, we will access the data stored at 1024. So what is the data stored at 1024? Since we have not stored it, it will return whatever the data was stored previously from previous programs. So that can be any garbage data. So the output here will be garbage. The output of this statement will be garbage. Although it will not be printed, this output will not be printed, but it will result in some garbage. Let's see the next command. It is C minus B. So what is the value of C minus B? C is 2024. C minus B, B is again 2000. So the value for C minus B will be same as this 2024 minus 2000 by 8, which is equals to 3. So again we will get output over here as 3. Next is star C minus A. So what is C? 2024. Star C is 1024. Now 1024 minus A. So what is the value? 1024 minus 1000 and divide by size. So size is 4. So it is 24 by 4, which is equal to 6. So the value that we have obtained is 6. And next is star star C. So what is the value of star star C? C is 2024. What is star C? Star C is 1024. And what is star of 1024? What is the data stored at 1024? See, 1024 is outside the given array. It's outside the array that we have allocated. So when we access that area which does not belong to us, we will get some data stored by some previous programs, which is garbage data. So the output of star star C will be garbage. Let's see the next command. It is star C. So what is C? 2024. What is star C? Data at 2024, which is 1024. We have one more star. So what is star 1024? 1024 is outside. So 1024 is garbage, and what is data at 1024? It is garbage. So we have some garbage data over here, and once we have done this 2 star, what we are doing is plus plus. So we are incrementing whatever that garbage value was there by 1. Let's say that garbage value was 4. So what we did here, that garbage was 4 and we made it increment by 1, we made it 5. Okay, so earlier this garbage was say 4. And by operating this expression, we made it 5. It will not be printed since there is no printf command, but we made the change at the location. Now let's see the next and last printf. What it is doing is C minus B. So what is C? C is 2024. 2024 minus 2000. Again we will get the same output, 3. Next is star C minus A. So C is 2024. Star C is 1024. Star C minus A, 1024 minus A. We will get the answer as 6. And last option is star star C. So C is 2024, star C is 1024, and star star C is, now this value at 1024, we have incremented it by 1. So earlier it was garbage 4, it is still garbage, but now it has been incremented by 1. So now it will be 5. So this is the final output of this program. So like this we have to solve such types of programs. These programs involve both the concepts of arrays and pointers. So whenever we are solving this kinds of program, we have to keep some things in mind. We have to keep in mind, first thing is that the name of an array represents the base address. Second thing we have to keep in mind is that whenever we are operating multiple operators like star and plus plus, we have to keep in mind their associativity and precedence. Like in plus plus and star, the associativity is from right to left. So whichever comes in right, that will be executed first, then which comes in left, and so on. And third and most important thing that we have to remember is that whenever we perform arithmetic operations like addition, subtraction on pointers or on memory addresses, then that does not mean that we are performing those operations on numbers. We are performing those operations on the memory locations. So it will not result in numbers. It will result in the number of elements in the array between those two addresses. So keeping these things in mind, we have to solve such kinds of programs. Thank you.